Alright, so this is the second part of Tuesday's office hours, November 1st. I've gotten some additional questions that I'll respond to in this set of office hours. So, specifically, I've got questions on problem 3, 5, and 6. So, we'll start with problem 3. You have a series-connected DC motor, and you're told what RA and RF is. And when driving an unknown load at 2100 RPM, the current is 5.7 amps. Voltage source VT equals 300 volts with a rotational loss of 0.4 newton meters. And you need to find the output power, develop torque. Well, once again, the very first thing we need to do is we need to find KKF. Now this time, you cannot find KKF from the magnetization curve because you're obviously not given the magnetization curve. However, you look at the formula sheet, you'll see that IA is equal to VT all over RF plus RA plus KKF times omega m. And you're told VT is 300 volts. You're told RF and RA. You're told omega m is 2100 RPM. And you're told that the current is 5.7 amps. So you know everything in this equation except KKF. So that's what you have to solve. You must find KKF before you move forward. Once you know KKF, you know that the developed torque has to be equal to KKF times IA squared. You just found KKF, you know IA, you know the developed torque. And then you have to find the output power. Well, we know that the output power has to be equal to the developed power minus the power due to rotational losses. Or, convert this into speed, we have omega m times the developed torque minus the torque due to the rotational losses. And you're told that the rotational losses are 0.4 newton meters. So you've just found developed torque, put in 0.4 newton meters there, you use your speed, and that'll give you your output power. So that's problem 3. All right. So the next one is problem 5 that I got a question on. So problem 5. So in problem 5, a series connected DC motor needs to provide 330 watts. So your output power is known, so you know P out, to a mechanical load. The magnetization curve for the motor is shown. If the input power is given as Pn is 430 watts, what is the speed of the motor, torque on the motor, and voltage Vt applied to the motor, assuming negligible rotational losses? Well, if there's no rotational losses, then our input power going in, Pn, well, you're going to have some loss due to the resistors. So here's your resistive losses. I'll just call it B resist for now. And that's the only loss you have before you get to your output power. So the difference of those two has to be the losses in the resistors. It has to be due to the conductive losses of the windings and the wires and whatnot. Well, the conductive losses are given on the formula sheet. So P conductive loss, which is your power going into your resistors. Same thing. I just changed my notation here before I pulled up my formula sheet. Is going to be RF plus RA, that quantity, times IA squared. And so in this problem, you know that these conductive losses, because there is no rotational loss, have to be just equal to P in minus P out. So the difference in that power has to be going into conductive losses if we just balance the energy. So RF plus RA, we know. We know that the P in, we know P out, and so we can use this to find or solve for IA. So we can determine IA from this approach. See what we're supposed to find. What is the speed, torque, and voltage Vt? So we know IA. Well, before continuing, we should find KKF, and we've done this before, so KKF, of course, is going to be the slope of the magnetization curve divided by the speed from that magnetization curve, as we've detailed before in class. So that allows us to find KKF. So, what else do we know? Well, we know IA, we solve for that, but we also know that the input power has to be equal to VT times IA. We know IA, so we can use the input power to find VT. We know the developed torque has to be equal to KKF, which we just solved for, times IA squared. So, since we know IA, we know the developed torque. And lastly, we have the speed is related to the torque from the equations from the formula sheet. So once we know the torque and KKF, we can find the speed. And so that's how we can do problem 5. So, problem 6. A permanent magnet DC generator has K phi of 3.2 Webers. So, you know K phi, telling it to you, and RA of 5 ohms. And so here's our EA. Here's our resistor, 5 ohms. And the prime mover rotates at a speed of 1370 RPM. So omega M is going to be 1,370 RPM times 2 pi divided by 60 to get it to radians per second. So we know the speed. Determine the no load voltage, full load voltage, and the torque required by the prime mover at full load if the full load power required by the load is 300 watts. So here's my load. And we know that the power going into that load is 300 watts. Well, the no load case would be when there's no load connected, which would just be EA. So VT no load is just going to be EA, which is just going to be equal to K phi times omega M. So that's the no load voltage. Full load voltage just means when we have this 300 watt demand coming out on that load. All right. Well, what's the power going into this load? Well, power going into that load would be the voltage across the load. That's what we're trying to find, this VT. That would be the full load. VT times IA, which VT is just going to be IA times R load multiplied by, of course, IA. So that's going to give us IA squared times R load. But we don't know R load. But we can express IA that we have here in terms of the EA, which we know, and the various resistances. And so let me go ahead and do that. So we know that IA has to be equal to EA divided by R load, which we don't know, plus that 5 ohms. And so I can plug that in. And let me do that on this next slide. And so I plug that into the square, this square expression. So I have P load then has to be equal to IA squared, which would be the EA squared all over RA plus R load squared times R load. Well, let's move this to the other side. So I can write this then as RA squared plus 2R load RA plus R load squared. And that all has to be equal to EA squared all over P load times R load. No, P there looks too much like an R, so I'm going to clean that up. So here I have a quadratic in terms of R load. So this term can be combined with this one to get me a quadratic. So I have R load squared plus a term multiplied by R load plus a constant equals 0. That's a quadratic. So I have two possible values for R load, as you might expect, because the question says assuming most of the power is delivered to the load. So you would expect that if I say something like that, you must have two answers, two possible answers. And so you have two values for R load. Well, when is most of the power delivered to the load? Well, most of the power is going to be delivered to the load when the load resistance is larger than RA. Because if the load resistance is smaller than RA, then most of the power has to be going into the load resistance for the same amount of current. Because the power going into a resistor is just the current squared times the resistance. And so if R load is smaller than this 5 ohms, then you're going to have most of the power absorbed by that 5 ohms. So we need R load bigger than 5 ohms. And so you pick that one. Pick that one. Once you know R load, then what else do we need? We need to find the full load voltage. Well, we know to get there, we can find IA. That might be the easiest way to do it. And the IA is going to be EAA divided by RA, which we know, plus R load, which we have just found out. And so we find IA. And then, of course, we know that the power going into the load, excuse me, not the power going though. We want the VT, the terminal voltage, is going to be IA times R load. So that's our full load voltage. And see, we got the full load voltage, and now we need the torque. Well, the torque is going to be equal to K phi, because there's no rotational losses, so we can just do developed torque is the same as the torque. K phi times IA. Now we know K phi, we found IA, we can get the developed torque. And so that gives us everything we need for that. Okay. So that is problem 6. So I'll see if there's any other questions that have been emailed to me here. So I got a question in terms of T out versus T dev. So these are more conceptual questions. Well, T out versus T dev, first of all, we have to be talking about a motor. Because for a motor, your output is torque. You don't have output torque when you're talking a generator. So T out equals T dev when you have no rotational losses, when you can neglect the friction, if you will, inside the motor. So that's when they're the same. Otherwise, you'd have to include the torque associated with the losses. So T out in general equals T dev plus T rotational, those rotational losses that may be present. A lot of times I neglect the rotational losses. They are physically present in most problems, but I usually neglect them to help keep the math a little simpler. P supplied versus Pn and P out. Well, once again, are you talking a motor or a generator? If you're talking a motor, then your Pn is going to be electrical. So that's going to be equal to the voltage times the current. If you're talking a generator, then your input power is going to be some sort of mechanical force. So then it would be the developed torque, basically, times the speed. P in versus P out, well, once again, are you talking what's the input, what's the output? If it's a motor, P in is electrical, P out is going to be the output torque times the speed. And for a generator, it's going to be the reversed. So for a generator, Pn is going to be some torque, and we'll neglect rotational losses for now, times the speed. And your output is going to be some current times some voltage. So it depends. Last question was on power supplied. The question there depends on what? Supplied by what? Are you talking about the power supplied by the source? In that case, it would be the input power. If you're talking about the power supplied by the motor, then you're talking the output power. So power supplied can go either way. So for power supplied, you have to look at the context. What am I talking about? Supplied by what? So in problem 1, I have torque supplied by the motor. And then you have the efficiency of power delivery to a mechanical load. So that would be power delivered to a mechanical load, or power supplied to a mechanical load. So that would be the output power. Problem 3, we talk about output power. Problem 5, we have the input power. The series connected DC motor needs to provide 330 watts to a mechanical load. So that's my output power. That's be 330 watts. Yeah, I think that pretty much summarizes it. So you have to keep track of context for some of these words. All right. See if we have any other emails that have come in discussing these issues. Okay. Nope, that looks like that's all the questions, so I'll go ahead and wrap up these office hours for now and get them posted as soon as possible.